Thank you. Well, firstly, thanks to the organizers for inviting me to be a part of this very interesting meeting. I must confess that I am myself learning a fair bit about quantum trajectories, which is a topic that I have not previously been exposed to in such detail. So yeah, I come from the Department of Physics at IIT Madras, and I'm part of the Center for Quantum Information, Communication and Computing there. So my own expertise is more in the area of quantum error correction, and this is a very recent foray that we undertook thanks to a postdoc in the group, Shrikant, who was actually here last week, whose background is on studying signatures of non-Markovianity in open quantum systems. And so it seemed like a natural line of investigation to ask about quantum error correction for non-Markovian noise. And in a sense, I think the last question maybe anticipated some of the things that I was going to talk about, which is exactly this framework where there could be certain intermediate times where you see non-Markovianity in the system through this information backflow and so on. And the question is, what would be a good error correction strategy in this scenario, right? So that's the kind of question that we are working towards. This work is on the archive, and I will not be going through all the details, so maybe I'll refer to this at various places. Okay, so this is just to be on the same page. This is sort of the more simplistic picture that one is used to in terms of system bath dynamics, where we often say that the system dynamics are modeled by a completely positive trace preserving map. Note that in getting to this CPTP map, E, we have assumed that this system environment state is initially in a product state of this form. It's rho S tensor phi E. And then, of course, there's unitary dynamics that governs the interaction of this big system, which is assumed to be a closed system. And then you trace out the bath or the environment degrees of freedom, and you get a dynamical map on the system degrees of freedom alone. And this dynamical map can be shown to be completely positive and trace preserving. And this is, of course, also what we call a quantum channel. And it's a kind of equivalent statement to say that if you have a CPTP map, then you also can describe this map using a set of operators, often called the Krauss operators, like so. So the evolved state of the system under the action of this map is basically given by this operator some representation, and these operators have to satisfy some constraint in order for this map to be trace preserving. What I've written out here makes the map trace non-increasing, and then if this is equal to 1, then it is trace preserving, right? So this, indeed, one can derive this dynamical map from the Lindblad master equation. But maybe before that, just a quick example, and this is a kind of circuits that we actually saw in David's lecture yesterday, and this is sort of a model of what a transmon qubit actually looks like, what the energy levels of a transmon qubit look like. And in this scenario, the decoherence mechanism can be modeled essentially via this Jaynes-Cummings interaction, which models the dissipation of a two-level system in a cavity, right? And I'll talk about this a little bit more, but just to again give a concrete example of this kind of a dynamical map and Krauss operators, this is one such example. This is what is called the amplitude damping channel. And like I said, this could, for example, occur in the context of energy dissipation in systems like transmon qubits. And this is also often called the T1 process, because this decay rate gamma out here is something that depends on time, and this time constant of this decay rate is what we call the T1 time. This is also often called the coherence time of the qubit in the literature. And these two operators, as you see, are they correspond to a particular physical process happening in the system. So if my system was in the excited state, it could decay down to the ground state with the release of a photon to the cavity, and the E1 operator essentially captures that. The E0 operator captures the scenario when this decay does not happen, and that happens with the probability 1 minus gamma, right? So these are the things that I've already said. So now, this sort of a picture that I presented, or even this one, assumes make certain assumptions, right? And so what are these assumptions? So first of all, like I said, it assumes that the system bath state is assumed to be in the product form. And more crucially, it assumes something called the Born-Markov approximation, which basically says that there is a large enough separation between the system and the environment timescales, and so long as the fluctuations in the environment, or rather the timescale over which the environment retains memory, quote unquote, is much smaller than the system timescales, then you can essentially ignore the effects of memory in the environment, right? You can essentially ignore these correlation effects, time correlation effects, provided there's a large enough separation between the system and Barth timescales. And there is also, of course, the rotating wave approximation, where the higher frequency terms in the Hamiltonian are typically ignored, right? So if 1 or 3 were to be relaxed, then we have a much more complex situation in our hands, where we may not even be able to describe the system evolution via a CP map. In particular, if 1 were relaxed, then it's not clear how you will have to essentially take, you'll basically not be able to remove your environment degrees of freedom so easily and talk about just the system evolution, right? If there was initial system Barth correlations. So we're not going into that. We're going to say that 1 and 2 hold, 1 and 3 hold, but we are essentially relaxing the Born-Markov approximation. And we say that maybe we are in time scales where the correlation effects in the environment do matter. And then what happens? And then it turns out that you can, of course, still write down a master equation. And this is the GKSL stands for Gorini, Kosakowski, Sudarshan, Lindblad. So there are 2 different papers. In fact, I should have cited a different one of Gorini, Kosakowski, and Sudarshan in '76, coincidentally, where they also write down this kind of a master equation. And so I'm not going to go into the details here, except to say that this L of t is what we call the Lindbladian. These Lj of t are the jump operators. We've heard about this in many talks here. And these sort of capital gamma j are the decay rates that we associate with each of these jump operators, right? And you notice that I have now put time dependences all over the place. And in fact, as the question that was asked towards the end of the previous talk suggested, if these gammas and L's were actually independent, if these gammas were actually independent of time, that there is a fixed decay rate, then we have a Lindbladian which is actually not dependent on time, and then we can write down the evolution in terms of this nice CPTP map, which forms a 1-parameter semigroup, right? So let me just show this on the next slide. So yeah, so suppose the gamma j are time independent, that is the decay rates do not depend on time, then the Lindbladian is also time independent, and then in this case, one can derive this dynamical map on the 6th system essentially as this exponential of t times the Lindbladian, and this is the quantum channel, what I described on the very first slide. And then, of course, the system state evolves like this. This forms a semi-group. This has a semi-group structure in the sense that I can always decompose the evolution over a particular chunk of time into smaller evolutions over smaller intervals of time. And I can keep doing this sort of ad nauseum. There's nothing that prevents me from zooming into the system for any sort of small intervals of time, right? And this is something that is very useful when we are trying to model sort of noise in quantum systems and try to do error correction on that, right? But of course, more generally, these gamma j's could be time dependent, and then this dynamical map actually is not of this simple form. It's this kind of time ordered integral that you get here, and this is no longer has a semi-group structure, right? So in this case, so this in particular is the kind of non-Markovianity that we will be addressing in this work. And essentially, this happens when at least one of the decay rates, so what can happen is, in this setting, okay, so maybe I should add a caveat here. So it could be that the gamma j's are time dependent, but you still get something called a time inhomogeneous Markovian evolution or time inhomogeneous Markovian behavior. Again, I'm not getting into that, but I'm going to address the sort of more pathological case where these decay rates can actually become negative for a certain interval of time, and then the dynamics is indeed non-Markovian. So non-Markovian in what sense? In the following sense, that the channel is no longer divisible in time, and in particular, it is no longer CP divisible. What do I mean by CP divisibility? So I say that a channel is CP divisible if I can break down this channel from T0 to T2 as the composition of two completely positive maps, one from T0 to T1 and the other one from T1 to T2. So this is something that's called CP divisibility. And of course, this breaks down when we have sort of these negative decay rates in the master equation, and this leads to this kind of a signature of non-Markovianity, where you could have intermediate maps, like the map from T1 to T2, being not completely positive, right? There's also a distinction that in the literature they make between positivity divisible versus CP divisible, etc. So we'll not get into all of that. So how does one see signatures of this? Well, very simply put, the corresponding Choi matrix for this channel for these intermediate times is not going to be positive, right? And this was something I think that was observed in a sort of experiment that was done with one of the IBM processors some time ago. So there's this reference which talks about quantifying non-Markovian memory in a superconducting quantum computer. So this is an effect that one does see in sort of the quantum processors, the real world quantum processors today as well, right? So let us look at these CP indivisible maps a little bit more in detail. So as I said, you have a non-completely positive intermediate map, but now you can go back and ask, well, the Choi matrix is not positive, but does it have any other redeeming features? Well, it turns out that the Choi matrix is actually Hermitian, okay? And so this class of CP indivisible maps actually can lead us to what are called hermiticity preserving, trace preserving maps, that is HPTP instead of CPTP maps. And it turns out that these maps actually lead to an operator sum difference representation, where you see I have, apart from the EI rho EI dagger, which I had earlier in my operator sum decomposition, I now have this additional sin I term, and this of course can be negative for certain intermediate times, and that's what makes these maps different from the standard CPTP maps. So in a way, this leads us to a class of maps which may not be too strange or too different from the CPTP maps that we know and love. But at the same time, there is enough complexity for us to ask questions about quantum error correction for these maps. Okay? Right, so there will indeed be certain intermediate times where this, so I mean, it is still a map, right, in the mathematical sense of a map, right? But whether it is a physical map for all times, that is the kind of question that you should be asking, and indeed it is non-physical for certain intervals of time. So in a way, what this tells you at this process is a bit like having a black box, which you can only query at certain times, and there are certain intermediate times where you simply cannot, you don't have access to what is going on inside this, but over a longer interval of time, it is still physical to probe this map, right? So I don't know if that answered your question, yeah. Right, so again, let's go back to this example, and now I'm actually showing you the Hamiltonian for this Jaynes-Cummings model. Again, this is something I believe everyone here is familiar with, so I'm just going to point out that consider the case where you have a single mode in the bath, and then the bath spectral density is a Lorentzian of this form, and your omega naught is basically the qubit energy gap, the delta is the detuning, B is the spectral bandwidth of the bath, and this capital gamma naught is what quantifies the strength of the system environment coupling. So I just want to show that this kind of intermediate non-CP-ness is something that could arise in a model like this. And so when you now solve for this using this time-dependent master equation that I wrote down earlier, you again get something that looks exactly like the amplitude damping channel, except now these damping parameters, which I had written down as simple exponential decay functions of time, are no longer that simple. They have a much more complex time dependence, and because of this much more complex time dependence, which now indeed depends on the spectral bandwidth of the bath, the strength of the system bath interaction, you can now identify regimes where this evolution is non-Markovian in the sense that was described in the previous slide. So now if this spectral bandwidth of the bath is much, much smaller than the system interaction strength, then it actually becomes one of these HPTP maps, that is this hermiticity preserving, trace preserving maps, right? On the other hand, the regime that we mostly work with is this, where the spectral bandwidth is much, much larger than the system-bath interaction. And so here it is the sort of time homogeneous Markovian, and there's a constant decay rate gamma naught, which is kind of the map that I showed you in the very second slide. So one can actually sort of plot this just to understand these regimes. So this is the damping strength as a function of time, and this is essentially time. You can think of it as in inverse units of the system bath correlation strength, that is the gamma naught. And so you see that there's a kind of dramatic difference. So I have fixed the spectral bandwidth here to 0.1, and the interaction strength is slowly dialed up from something very small to something very large. And indeed, there is a kind of crossover point at which this damping strength, which had, so this is, I guess, your exponential sort of behavior of the damping strength gamma, it starts oscillating. And then if you're in this deep into this non-Markovian regime, which is basically very high degree of system-bath interaction, then you see these very rapid oscillations of the damping strength. You can also play this game the other way around, where you fix the system-bath interaction strength and then you play with the spectral bandwidth of the bath, and similarly you can see these effects. This is just to say that one could indeed probe or access these kind of effects by tuning these parameters accordingly, like playing around with these B's and the gamma naughts, all right? Okay, so this is kind of the model that we are going to look at. And now what does quantum error correction have to say about this kind of a noise regime or this kind of a noise model? So again, this is sort of the obligatory introductory slide on quantum error correction, just so that, so again, yeah, just to sort of be complete. So imagine that you just have bit flip noise on the system. So this is basically saying that you could, your qubit could flip with some probability p or not flip with probability 1 minus p. And then what an error correcting code does is first you have an encoding, which basically says that you have to map your system state onto the state of a larger Hilbert space, but onto a specific subspace of the larger Hilbert space. And this is the specific subspace that's chosen here. And so you've gone from these physical zeros to the logical 0 and the logical 1. And the span of this logical 0 and logical 1 is what we call the code space. And the reason that this works as an error correcting code is because bit flips on different qubits, so single bit flips on different qubits are actually distinguishable, and therefore they can be detected and corrected. And then since the noise is essentially of a sigma x, once we have detected, we know how to correct, which is basically again to apply a sigma x. So this is a kind of schematic of this. And of course, there is some threshold probability up to which this scheme is going to work, right? So here's the same schematic again just some definitions. So I say that a quantum error correction protocol is essentially characterized by the code, the choice of code, which is what's called the encoding here, and also the choice of recovery map, right? Now, in this picture, I just have syndrome extraction followed by some classical feedback, which tells me what correction I need to do here. But I could think of abstracting out this whole sort of area and calling this whole thing a CPTP map, right? And this is sort of what we are going to do. Now, if one is interested in correcting for Pauli errors, then this recovery operation is simply the inverse of the noise operator, which is also a Pauli. So then you can sort of break down that more general picture down to the simple picture of syndrome plus a unitary operation on the data qubits or the encoded qubits, okay? But if one wants to look beyond Pauli noise, like the kind of model that I have been talking about, namely this amplitude damping, what can one do? Well, you can still discretize your errors in terms of the Paulis, right? And you still use a Pauli error correcting code because you have a linear theory of quantum error correction, which tells you that if you have corrected for x and z independently, then you have also corrected for y. And then by extension, you have corrected for arbitrary single qubit errors, right? However, is it the best strategy, or is there something different that one can do? Well, first of all, note that if I'm looking at something like amplitude damping, then in the Pauli basis, it looks like this. And you notice that the damping operator is a combination of x and y, and the no damping operator is a combination of identity and z. And this kind of picture is somewhat different from the Pauli noise models that one studies, where you usually assume that there is an identity operator in your description of the error set, in the sense that with some probability nothing happens, and then you have X, Y, Z, etc. occurring with certain probability. So here you do not have an operator which is simply a scaled version of identity, nor do you have simple scaled versions of Pauli's, of course. So if one sort of sticks with this picture of discretizing the errors in Pauli's, in terms of Pauli's and correcting them, then you get a bound on the resources that you need to do error correction. And on the other hand, if you move to correcting sort of directly for amplitude damping noise, then it may be possible to beat this bound, and this has been known for a while. So in fact, a 4-qubit code was constructed tailored to amplitude damping noise, which provides a degree of protection or a fidelity that is comparable to the 5-qubit code. And this kind of idea is what we will call noise-adapted quantum error correction, where the idea is to think about designing quantum error correction schemes that are tailored to specific noise models as opposed to general-purpose error correcting schemes. So here's the 4-qubit code, and notice that this also has associated with it a set of Pauli stabilizers. However, this is not a stabilizer code, because the noise operators, which in this case are your damping operators, are going to map the code space still to distinguishable parts of this larger Hilbert space, but they are no longer simple unitary transforms of the code space. In particular, although I have identified a set of stabilizers here, it turns out that just measuring this set of stabilizers is not enough to decode for this for the amplitude damping noise on this code. In fact, I have to measure additional so-called secondary syndromes which actually do not commute with the stabilizer generators. So what I'm trying to get at is, if I'm trying to do this noise-adapted error correction, then I may have to do non-trivial decoding or recovery operations, like, for example, non-stabilizer measurements, or more generally, I could think about the recovery operation itself as a CPTP map, and then ask what is the best such CPTP map that I can construct for this specific code and this specific noise. Just to complete the story with the 4-qubit code, this is the fidelity that one achieves with the 4-qubit code in terms of the damping strength gamma, which I have shown you in previous slides. And of course, you notice that the linear order term in gamma is gone, and so you've corrected all the single damping effects. And you notice that you have a fidelity which is actually maybe even better than your 5-qubit stabilizer code. Okay? All right, so this is sort of the picture. This is the perfect error correction picture, and then there are certain algebraic conditions that you have to satisfy in order to fit into this picture, right? So if I have to pick a code, then it has to kind of satisfy this condition with the noise operators. And if this is satisfied, then we know how to construct the recovery as a syndrome extraction followed by a unitary. Now the 4-qubit code, however, does not fit into this picture. It actually fits into a more general picture like this, where the noise could map my code space to sort of overlapping parts of the larger Hilbert space. Not just overlapping, but also kind of somewhat randomly deformed spaces in this larger Hilbert space. And algebraically, this can be modeled as adding a perturbation term to the perfect quantum error correction condition, where now the lambdas in the original condition and here are scalars, but the bij's are actually matrices or operators on the code space. And of course, in this case, like I've been saying, these error spaces are not orthogonal to each other, and they're also non-unitary deformed versions of the code space. So in this case, one can actually ask interesting questions about what is a good noise-adapted recovery that one can use in order to error correct in this scenario. And the example being that we have in mind is something like the 4-qubit code with amplitude damping noise. So I just want to talk about the recovery scheme that we use. Of course, I could ask this question in a completely numerical way and then make this an optimization problem and say, okay, here's a code, here's the noise, tell me what is the best recovery map that I can construct for this, which gives me the best worst case fidelity, which is a particular metric that we use. So this is a computationally hard problem, but a while ago we came up with an interesting analytical solution for this, which says that you can define one such CPTP map called the PEDS map, which actually has its Krauss operators defined like this in terms of the Krauss operators of the noise itself. And with this analytical construction, we showed that this construction maps back to the perfect case in the limit that you have a code which is perfectly correctable for this noise, which is nice. And then for any arbitrary code and noise, this achieves a worst case fidelity which is close to that of the optimal recovery channel. So it does not solve for you the problem of the optimal recovery map, but it says if there exists a very good recovery map, then the PETS map is going to achieve a worst case fidelity which is close enough to that very good optimal recovery map, right? Another interesting point to note is that the action of the noise followed by the PETS map actually leads to what's called a unital map or a unital channel, which is one that preserves identity. And this is kind of a nice feature to have for the recovery map. So I guess now I'm going to put all of these things together and say, well, I have this kind of a noise adapted recovery, and I have this amplitude damping noise, and I have a code which is tailored for amplitude damping noise. But now how does this all come together in the non-Markovian regime? Okay. Any questions on the recovery or the noise adapted scheme? Okay, then I will proceed. Okay, so in general, well, what about quantum error correction in general for non-Markovian noise? So I just want to point to a couple of works which talk about some potential issues that can arise when one is doing quantum error correction in the non-Markovian noise regime. This is sort of an older work by Oreshkov and Brun, where they actually study something called continuous time quantum error correction, and they actually study this for the case of non-Markovian bit flip noise. This is exactly the same noise model that I introduced error correction with, and the same 3-qubit code, right? So I guess the question that they're trying to address is, if I just use the conventional 3-qubit code, but my noise is now non-Markovian bit flip noise, then how well am I doing? Well, it turns out that this, what I'm plotting here, what they've plotted here is the code word fidelity for the all zero state. And this is again time. Here they've incorporated the noise trend, so the units are different. So they show indeed that there is a drop of this fidelity all the way down to 0, and this is sort of after error correction, right? Whereas normally you expect, or you say that your error correction scheme is successful provided it keeps your fidelity above 0.5, right? And anything that takes you to below 0.5, it's really not worth the effort to be doing quantum error correction. So what this says is there are time regimes where if you have non-Markovian noise, then your fidelity even post error correction can actually drop all the way down, right? And there's more recent work, and this is from Shabani's group, and this is very recently from Mark Bayard's group, which goes a little bit into the theory of this algebraic theory of quantum error correction, and says, can one just translate that theory to non-Markovian noise regimes? In particular, can I take the same Knill-Leflam condition, which I wrote down for the case of CPTP maps, and can I adapt it to these HPTP maps? And their answer is actually no. And they say that, okay, so remember I spoke about this intermediate time non-CP-ness. So such maps can actually be represented like this, where, like I told you, it's an operator sum difference representation, which means I can represent this map as a difference of two positive maps, as a difference of two completely positive maps, okay? And if I now take a code that satisfies the Knill-Leflam conditions for the case of just the EIs without the sign I, meaning the sort of the Markovian version of the same noise, then it turns out that you may actually no longer be within the domain. Oops, I'm sorry, I'm missing. Okay, yeah. So it turns out that this code space may actually no longer be in the domain of E. A simple way to see that is the following. So if I've now taken a code which works for Markovian EIs, and then I kind of work out the quantum error correction conditions for this case, and then if I have non-zero support in this part, which is sort of giving rise to some negativity out here, and then if I do the syndrome extraction and all of that, I may actually end up with negative probabilities, right? So I actually cannot do syndrome extraction for this kind of a procedure. So it turns out that they then work out a modification of the Knill-Leflam condition, which has to be incorporated if one wants to address these kind of effects in the standard quantum error correction framework, okay? All right, so, but suppose I just sort of forget about all of this and simply say, okay, let me just take this non-Markovian amplitude damping noise, I run the 5-qubit stabilizer code, what happens? Well, it actually doesn't do very bad, right? So this is now the fidelity as a function of time, and the line in black is basically the case where I don't do any error correction. The line in red is where I have done error correction using the standard 5-qubit stabilizer code and using stabilizer recoveries. Of course, you notice now that your oscillations, which existed in the raw qubit case about 0, I mean, sort of take you all the way down to 0, have actually are now oscillating about 0.5, right? So presumably, this 5-qubit stabilizer code actually does not run into the kind of issues that one spoke about on the previous slide, where you could have non-zero support on this negative part of the NCP map, and then you could actually end up in a very unphysical scenario, right? But the question that we were asking is it possible to sort of write down a recovery strategy or an error correction strategy where one doesn't have to worry about this, and where one can say that for any sort of HPTP map, this error strategy actually works, this recovery strategy actually works, right? And so that is what we do in this paper. We actually show that it is possible to define the same PETS recovery map, which I spoke about a couple of slides ago, for the non-Markovian case. Now, if one wants to adapt the recovery map to noise, you can do it in two ways. You can think about doing it with these NCP nets taken into account, and so you actually end up with a non-Markovian recovery map, or you can actually adapt it to the Markovian regime of the noise. So in the second case, you're not exactly adapting the recovery to the noise, but you're actually adapting it to a particular regime. You're adapting the recovery to the structure of the noise, but not to the noise strength, which is in a way nice because your recovery is no longer dependent on the noise strength. It's a fixed recovery. So we show that both of these strategies actually work, and there is some sort of analytical results that we show, but I'm going to skip this, and I'm just going to show you the pictures. So this is what we find. So this, of course, the black line is the raw qubit with no error correction. This is again subject to non-Markovian amplitude damping noise in this regime, etc. And the code that we are using for all the other plots is the 4-qubit code. And if you look at this red line, that was your stabilizer recovery, which I showed you, which was not doing so bad. But then now you look at the 4-qubit code. So by the way, the stabilizer recovery is with a 5-qubit code. But now these two, the blue lines, the light blue and the dark blue, are basically for the noise adapted code, or the approximate, the 4-qubit code, and the noise adapted recovery map, both Markovian and non-Markovian versions of this. And then you see that that actually does better than the 5-qubit code. And in particular, if I were to exactly adapt this recovery to the noise, then I'm actually above this 0.5 fidelity for all times. We see this little interesting oscillation when we actually adapt the PETS recovery to the Markovian regime of the noise. And we did a little bit of analysis to see why we see these additional sort of oscillations here. And it turns out that it goes back to this unitality business that I spoke about. So if I adapt my PETS recovery exactly to the noise strength at all times, then the combined channel noise plus recovery is unital. And so it kind of preserves the center of the Bloch sphere, if you will. And so if at this very high degree of noise strength, you kind of hit the center of the Bloch sphere, then you kind of preserve that point, right? But which is why you see this kind of flattening out here at the 0.5 or just above the 0.5. But if now your recovery is not exactly adapted to the noise strength rather, then it turns out that this combined map of the noise followed by recovery is no longer unital, and there is what we see a little bit of a revival in the fidelity plot even in the Markovian regime of the noise, and that kind of just carries over to the non-Markovian regime as well. And so we see these sort of additional oscillations when we work out a Markovian version of the PETS map, which is adapted to noise strengths in the Markovian regime. Okay, so I think that pretty much is a story that I wanted to tell you. We've done a few more studies. So we asked, for example, what about different codes and the PETS map? So what happens if you increase the system dimension? Do you start doing better or worse? And then we actually see that in sort of all, so it turns out that actually this 5-qubit code with a PETS recovery rather than the syndrome recovery actually does better, because in a way you're adapting the recovery to the structure of the noise. So I maybe skip this. This is to say that one can think about other noise-adapted strategies, and some of them actually don't do well at all. So this red line out here is what's called this long recovery, which is another noise-adapted recovery that one could construct. And that one actually, the fidelity drops all the way down to 0. And again, we have some analysis which understands why that happens. Okay, right? So let me just stop here and say that. Yeah, so there seem to be aspects of perfect QEC which may not immediately or directly carry over to the non-Markovian regime, and that kind of motivated our investigation to see if noise-adapted quantum error correction can provide some solutions in this area. And so we indeed show that there exists a way to construct this recovery in a noise-adapted way for arbitrary codes and channels, which kind of spans the whole range from the Markovian to the non-Markovian regime. And in the process, we also actually have a sufficiency condition, which is kind of all the algebra that I skipped on one of the slides. Yeah, okay, so I think I say this here. And well, so going forward, what can one do? So it seems like it's possible that we can come up with circuit implementations of this PEDS map. So one could kind of ask if for this version of the map where we are adapting it to specific noise strength regime, can we then come up with good circuits and sort of demonstrate some of these fidelity curves that we show. But more generally, there is this sort of mathematical question you can ask, which is, how does one really generalize the framework of error correction to take into account sort of general non-Markovianity in general? And there seems to be some interesting ideas from this so-called process tensor formalism, which was recently introduced to talk about open system dynamics. There's also some recent work from Kishore Bhatti's group on what they call a strategic code, which kind of extends this idea of space-time quantum error correcting codes to the non-Markovian regime. And then, of course, one could also think about now simulating this exactly. And I've really only spoken about like single shot error correction in some sense. So what happens when you really have repeated cycles of error correction? And that's where the system path correlations over long times may actually start becoming important. So it may be interesting to do some simulations. And there's again been some recent work along these lines. So let me stop here and happy to take questions.
Hey, thanks for a talk. Yeah. Just a few questions. So this non-Markovian PEDS map you can't do, right? Because it's not.
Yeah, okay. You can't do. Yeah. So that's the reason we.
You focus on, you asked this question.
Yeah, exactly.
Now, can you go back to these simulations? Maybe the first. So these are simulations. Yeah, like of the like this. Yeah. This is simulating the non-Markovian noise, not with this this sort of non-physical map, but just fully. The way it affects the dynamics.
So basically you now, so you assume that you have this, the same amplitude damping channel from whatever time to whatever time, except that now your gamma is, as I remember I told you that the noise strength is a function of the B and the,
so you make it negative.
These are set to the non-Markovian regime.
Oh, okay. But so you're not sort of simulating the non-Markovianity by including the environment, because then I have a question. In the sense that you're saying I'm representing the non-Markovianity by this sort of unphysical process, right? So are you sure that that is exactly the right representation in terms of what the noise does to the system, right?
Yeah.
You could say, because there are results that if you say have non-Markovian noise, then you say, oh, I just have to treat the system unitarily, and then there may be a loss in terms of, you have to look at the amplitude of errors instead of the probability, so you may lose a square root of factor.
Right.
But you like to kind of claim that this representation is sufficient to cover the behavior.
Exactly. No, we are not looking at the full open system, right? We are indeed saying that it is still possible for me to look at just the system map, right? I can write down a system map. Like I said, it is mathematically defined, right? And I'm looking at the system map in a regime where I know that this is non-Markovian in the sense that I see these, one signature could be that I see these revivals as a function of time.
Right, but you also know that because the system map is not CPTP, it cannot be exactly the dynamics.
Yeah. So it's my answer to that would be that it's possible that we are not capturing fully the non-Markovianity of this system bar dynamics, but I feel like we're certainly addressing certain aspects of it which one can see by tracing out, by still looking at just the system map alone.
Yeah, I mean, I can readily believe that it does capture, but it is sort of a separate question, right?
Yeah, because I agree. I agree that it's true. So that's kind of the reason I put this last point at the end, where actually what would be interesting to do is to simulate the whole thing with the error correction process, and then sort of look at the same sort of fidelity behavior.
Right, and then you can confirm, because that's also maybe just the last question. This thing that you mentioned, the result by LIDAR. Because it sounds like. But you're applying a non-physical map, and then you apply a real recovery, and then you can't find a real recovery. Well, that's maybe not so surprising, because the point is, how do you meet the quantum error correction conditions? You say, oh, the map happens, and then there must be a recovery that gives you the initial density matrices.
Yeah.
But the first map that you apply is not physical, so why would you?
No, but I think
that's not maybe the point they're making.
No, in the Oreshkov-Brun paper, they actually are doing the same 3-qubit code recovery, but their framework is a little bit different. I must add that caveat. So it's a continuous time error correction framework, where they actually add this correction term to the master equation itself.
Yeah.
Right?
And I understand.
Yeah. So, but then I think the recovery is still physical in that setting, right? Because
well, I was more thinking about LIDAR, but I can ask after.
Sure.
Thanks.
Hi.
Sorry. Hi.
Correct me if I'm wrong. So what I understood is the non-Markovian amplitude damping noise is on the individual physical qubits, right?
Yeah.
And then you implement the error correction code on the logical qubits, which does the entire recovery.
Yeah.
So my question is, are you proposing any scheme also to protect the individual physical qubits from this sort of non-Markovian noise? Because dynamical decoupling is a scheme that is very effective against non-Markovian noise.
Right. So in the error correction framework, we always kind of ask this question about, it's not so much about protecting the physical qubits as it's protecting about a certain amount of information, like the amount of information that could be encoded in a qubit, or the amount of information that could be encoded in some k qubits or whatever, right? And so you're not really asking about, I guess the question you are asking is more, I would say, along the lines of stabilizing the individual qubit, and indeed so, but I would make a distinction, and I would call that as error mitigation rather than error correction, in the sense that you're now doing something at the single qubit level periodically to make sure that it stays within the sort of the superposition or the place where you want it to be in the block sphere, right? So yeah, indeed, I do think that Kavan Modi has some work on this, on dynamical decoupling for non-Markovian noise. I don't have the reference here, but it's probably there in our paper. So yeah, indeed, there has been some work on doing dynamical decoupling for these kind of non-Markovian models. Yeah.
Thank you so much.
Yeah.
Maybe one last question.
Thank you. I have maybe 2 last questions, actually. One might be naive, just to check if I've understood this right. So you're modeling time-continuous noise, basically. And what these graphs show, if I'm not getting this wrong, is this would be the fidelity if you were to stop it at the time on the x-axis and to apply the single recovery.
Right, absolutely.
At that point, right?
Yeah.
So is there a reason that you wouldn't get to pick your perfect time in this? Because why would you do that if you know what your noise is at the point where the noise looks particularly bad?
Right. So, I mean, as an error corrector, I would like to know, for example, indeed, but I would like to first know how my protocol works for different times, right? And if I'm planning to do this and eventually run a quantum computing and all of that, then I may not have control over the length of time for which I'm running a particular quantum circuit, or where exactly I get to do this error correction intervention, right? So when typically we do these fidelity plots, we try to ask this question for all time, or so for enough sufficient length of time, so that we know at what point indeed the qubit stops being anything like what it is. Yeah.
So you want to be able to do this more generally without so much knowledge of the system. That relates to my second question.
Okay.
Is this, so you're motivating the form of noise that you're using here by this, in a sense, being mathematically convenient, because you get to just put a time dependence in the prefactors in the master equation. Is this a good model of noise? This is hard to test, I think.
Right.
And the other way around, would you be if you chose a convenience on the side of the recovery, a mathematical convenience, for instance, a way where you can get good PETS type maps, but you do away a little bit with being able to do something mathematically conveniently on the side of the noise? Would you be using the same methods then?
So to answer the first part, yeah, I mean, it's indeed true that this was a kind of convenient noise model, and we found exactly this kind of non-Markovian version of the amplitude damping noise, which we have studied for a while now, and so it was kind of easy to pick this choice. Well, arguably, it is somewhat physical, because like I said, when you think about many of these two-level systems with a bath, then this dissipation is kind of the natural model, and then indeed, it's not guaranteed for you that all these decay rates are going to be time independent, so there is bound to be some non-Markovian version of amplitude damping noise that occurs in real physical systems. So that's kind of my argument for the choice of noise model. Your second question was, can you tweak the noise model, or can you, I didn't quite understand, so my error correction is, my error correction is kind of time discrete, in the sense that there are specific times at which I'm doing this recovery map. So the way I'm asking this question is, if I have this noise model, then what is the best recovery strategy that I can do, right? And I guess you're saying, can we turn this around and say, if this is the recovery strategy that I can do, then what kind of noise does that correct? Or is that, am I understanding the question? Yeah, we should.
Wondering, you require a Hermitianic preservation.
For this, okay. Right. Yeah, indeed. No, so we do need this kind of operator sum difference representation for us to be able to even define the PETS map. That's absolutely true, and indeed I should say that. If we do not have this, if we have some arbitrary form of non-Markovianity, then I do not know what one would do, right? And that kind of was the last point on my final slide, where I said, one may have to move away from this algebraic framework altogether, and maybe this process tensor or some other framework actually helps us model this better, right? I think Sai had a question, and since he's an old friend, maybe
one true last questions.
Yeah.
I'll try and keep it quick. So this difference of maps, it also shows up in many other places, right? Like if you do, for instance, hypothesis testing, you always end up with like the difference of two states or the difference of two maps.
Okay.
And usually the strategy is to project out onto the positive part of the. So that kind of a strategy, if you use, do you see something that is different from this?
So then you would not be actually correcting for that noise process, right? But that's not something we have actually done here. But in a sense, it seems like you're by hand removing completely a certain part of your noise model and sort of looking at. But we haven't actually done that. So
can I just ask just one last question, which is, what is the actual, in Google or IBM, in the kind of existing architectures of quantum computing, what's like the most dominant non-Markovian noise that people would worry themselves with? Is it burst adjacent, or like, is there some reason that,
maybe some of the experts, yeah. I think that's kind of the work that I was referring to, this Kavan Modi's work, where they actually demonstrate this on an IBM processor and show some improvement and so on. Yeah.
And maybe it's a discussion that can be pursued over lunch. So thank you very much again for your talk.